Yes, yes, thank you very much. Yes.
Please speak up.
Oh, okay, okay, understood, Sensei. Okay, thank you very much. Good evening, everyone. First of all, I would like to thank all of you for your presence. My name is Salman. I'm a Shaikh and I'm a third-year PhD student. And today I'm going to present my research work on a study on distance-based outlier detection on uncertain data, advised by respected Kitagawa sensei. Here's the outline of my today's talk. So I'll start with the introduction and background. Then I'll talk about the problem definitions that we are discussing in this dissertation. Then I'll talk about the related work and research contributions in this dissertation, which are 3 listed here. And then I'll conclude my work. So starting with the introduction and background. First of all, what is an outlier? An outlier is a data point which is quite different from the remainder of the data in the data set. And it was formally defined by Hawkins in 1980 as an observation which deviates so much from other observation as to arouse suspicion that it was generated from some other mechanism. As far as applications of outliers are concerned, since it's a fundamental problem in data mining, it has several applications in several domains, including in network intrusion detection, credit card fraud detection. It's also used in identification of malfunctioning sensors, industrial damage detection, and so on. So due to its importance in data mining, several outlier detection approaches have been proposed in past, including distance-based, clustering-based, density-based, classification-based, and some statistical as well. Here in this work, our focus is distance-based approaches, because distance-based approaches are the simplest and the most basic one, and they can be used as the pre-processing step before applying more advanced and application-specific outlier detection techniques. As far as distance-based outlier detections is concerned, there exist several definitions given by different authors. So here I am listing 3 of the famous definitions. In 1998, Knorr defined for the very first time distance-based outlier, and according to them, outliers are the data points which, for which at least fraction p of the objects are outside the distance t. In 2000, Ramaswamy defined outliers as the data points whose distance to their kth nearest neighbor is largest. In 2002, Anguly defined in a slightly different way that outliers are the data points whose average distance to their k nearest neighbor is largest. In this work, our focus is the first definition, that is E.M. North's definition, which was given in 1998. So I'm going to describe this definition with an example. As I defined that an object O is a distance-based outlier if at least fraction p of the objects are outside distance d. So here I give an example. Consider a data set consisting of 10 objects where parameters p and d are specified by user. Here in this case, object O6 is likely to be an outlier because majority of the objects are outside the d distance of object O6. Recently, due to the advancement in data collection technologies, there's a vast increase in uncertain data, both uncertain static data and uncertain data streams. This type of data is actually generated by sensors, GPS, and also from moving objects. There can be several causes of uncertainty. Some of the causes include like limitations of equipment, sometimes delay or loss of data in transfer. Sometimes uncertainty is induced intentionally to increase the privacy of the data. Uncertainty can be broadly classified into two, and into like tuple level uncertainty and attribute level uncertainty. Tuple level uncertainty is the uncertainty in the existence of tuple in a data set. For example, in this particular table on the left, you can see with each and every tuple there is a confidence of appearing in this particular data set or in this particular table. So this is what we call the existential probability of each tuple. On the right hand side, we have a table with attribute level uncertainty, where the uncertainty lies in the individual attributes, which is usually modeled by some specific probability density function or sometimes by variance. So in order to get reliable results from such data, uncertainty needs to be considered in calculation. Here in this work, we propose outlier detection from uncertain data with attribute level uncertainty. Here is a quick survey of different outlier detection approaches on deterministic data. As you can see that for each and every approach there exists a lot of related work. But as if you look at the existing and existing approaches of outlier detection on uncertain data, there are quite a few approaches that have been proposed for both attribute and tuple level uncertainty. Here in this case, we propose two of the outlier detection approaches on static data and one approach on data streams, and all three approaches deals with attribute level uncertainty. So I will be discussing about more on the related work in the next section. So here's a quick summary of our contribution in this dissertation. So in this dissertation we propose UDB outlier detection on uncertain static data. And in this work we have used cell-based approach to index and tune the dataset objects. We also propose top K distance-based outlier detection on uncertain data. Here in order to increase or improve the efficiency of outlier detection, we use populated cells list or PCL list. Finally, we propose outlier detection techniques on uncertain data streams. And in order to improve the efficiency of outlier detection in this technique, we propose incremental processing. So I'll be discussing about each of the problem in the future sections. So now I'm going to define these problems formally. The very first problem that we are dealing in this dissertation is about UDB outlier detection, and it can be formally defined as an uncertain object is a distance-based outlier if the expected number of objects lying outside the d distance of O are at least fraction p. Here, assuming here in this work, uncertainty of object is modeled by the Gaussian distribution. So assuming that we have 10 objects in the data set where the parameters P and D are specified by user. So in this particular example, object 06 is likely to be an outlier because the number of D neighbors or the objects lying within D distance of object 06 is the smallest. Our next contribution is about top K outlier detection from uncertain data, and here our aim is to find K strongest outliers from the data set. And we find this by finding the D neighbors or the outlier score of each and every object in the data set, and the top K objects are selected as the top 2 outliers with respect to their number of D neighbors. Our final contribution is about outlier detection on uncertain data streams. And as we know that moving objects change their states over time, and these states arrive as time series data streams, as we can see in this particular table. Here T1, T2, and these denotes the time stamps, and S1, S2, and so on denotes the sets of the attributes. We call them state sets. And A denotes the attribute vector, which denotes the state of an object at time Tj. So here we define continuous outlier detection as an uncertain object O is in a state set Sj is an outlier if it differ greatly from other objects in a state set at time Tj. Next, I give an example or real-time application of our method. So for that, our application is about identification of malfunctioning sensor, and for that we have used a data set from Intel Berkeley lab obtained from 54 sensors. So in this figure, the black dots denote the sensors, and these sensors are generating room temperature and humidity values. And these values are generated each epoch, where epoch is 31 seconds. So in order to detect outlier from such data, we have used CUDB or continuous outlier detection techniques for 500 consecutive epochs. And the sensors generating the outlier values in majority of the epochs are identified as outliers. Here we assume that it's greater than 50%. So we identified 2 outliers, that in 18 and 24 with the experiments. Next, I'll talk about some of the related work on uncertain data, outlier detection on uncertain static data. Outlier detection on uncertain data was first of all given by 2008 by Agarwal. And they gave subspace or density-based outlier detection, and according to them, an uncertain object is an outlier if the probability of existence of O in some certain space with some specific density is less than some user-defined threshold. In 2012, Matsumoto extended Agarwal's work by providing a parallel version of Agarwal's algorithm using GPU. And they also used OpenCL framework for programming GPU kernels to speed up the or to parallelize the outlier detection of Agarwal's. However, both of the works focuses on density-based outlier detection, whereas our work focuses on distance-based approach in full space. Hence, the problem definition is quite different. Distance-based outlier detection on uncertain data was also studied by Wang in 2009, and they considered uncertainty in the existence of tuple, or we call existential uncertainty. So in their work, each tuple is associated with the confidence to appear in a data set. However, in our work, we consider uncertainty in the attributes values. In 2011, Jiang also gave an outlier detection of uncertain data. In their work, outlier detection is based on the object's instances. And an uncertain object consists of a lot of instances where each instance is modeled by a probability density function. So objects instances with similar properties are considered to be normal, and an object is identified as an outlier if most of the instances of particular objects are outlier. However, in our work, outlierness of an object depends on the number of D neighbors rather than the instances. Next, I'll talk about some of the related work on uncertain data streams. The very first work on uncertain data streams, on outlier detection of uncertain data streams, was given by Wang in 2010, and they considered tuple level uncertainty. And in order to improve the efficiency of outlier detection, they made use of outliers detected in the previous windows to detect outliers in the current window efficiently. And in 2012, recently, a slight variation of Wang's work was given by Gao, and they considered actually the tuple level uncertainty as the Wang's work, but in their work they considered tuple instances rather than tuples uncertainty. So tuple outlierness now depends on its outlier instances rather than tuples itself. Both of the above work deals with tuple level uncertainty. However, in our work, we deal with uncertainty in the attribute values. So the overall motivation of our proposed work in this dissertation is to enable distance-based outlier detection from uncertain static data and uncertain data streams, and to speed up the outlier detection process from uncertain data by using cell-based approach, PC list-based approach, incremental algorithm, and so on. Next, I'll talk about first of our contribution, that is UDB outlier detection, and in this work we propose two approaches of outlier detection. So in the first approach, UDB-CG, or uncertain distance-based outlier detection using conventional Gaussian uncertainty. Here the attributes of the uncertain objects follow the conventional Gaussian uncertainty. Next, we give an approximate approach using bounded Gaussian uncertainty to speed up the outlier detection process. So here's again the review of the same definition that I discussed previously, that UDB outlier is defined as an uncertain object is a distance-based outlier if the expected number of objects lying outside the D distance of O is are at least fraction P. So here, as I gave an example previously, object O6 is likely to be outlier because the expected number of objects lying within D distance of object O6 is the smallest. Now I'll give some preliminaries. We assume the GDB as our data set of uncertain objects, and we assume that the attributes of uncertain objects follow Gaussian distribution. Moreover, we assume that objects' attributes are uncorrelated and its standard deviation are uniform in all dimensions. However, a statistical procedure called principal component analysis, or PCA, can always be used to transform a correlated Gaussian distribution into uncorrelated one. So this assumption does not limit our work to only uncorrelated attributes, and we can use it for correlated as well. Next, PR, OI, OJ, D, or PR alpha comma D denotes the probability that two objects lie within D distance of each other, and this is actually computed from the distribution of the difference of two objects' attributes, and this is how it is computed. Next, hash D neighbors denotes the expected number of objects that lie within the D distance of any object OI, and this theta denotes the threshold, where n is the number of dataset objects and p denotes the fraction of objects that lie farther than D distance of an object OI. Here we give one lemma approximate probability values, which we would be using to explain our further contributions. If the attributes of two objects follow the Gaussian distribution, then their difference also follow the Gaussian distribution. Assuming that alpha denotes the ordinary Euclidean distance between the means of two objects, then if alpha is less than or equals to d minus t sigma, or the Euclidean distance between two objects is less than or equals to d minus t sigma, then this probability is approximately equals to 1. On the other hand, if this alpha is greater than d plus t sigma, then this probability is approximately equals to 0. So where t is taken large enough to enclose the large amount or the large portion of the Gaussian distribution, say greater than 99%. So here is an example of what is UDB outlier detection, the naive case. So as we know that an uncertain object is UDB outlier if the summation of probability that an object OI lie within d distance of all other objects in the data set. So here in this case, object O4 is an inlier because this summation of probability is greater than threshold. On the other hand, object O6 is likely to be outlier because this summation of probability is less than the user-defined threshold. The naive approach of the UDB outlier detection is to make use of nested loop to find the number of d neighbors of each object in the database. However, on average it takes O(n) square costly probability computations, where one probability computation is quite expensive. So naive approach is too costly for such a solution. So here we propose a cell-based outlier detection to reduce the number of costly probability computation. So here I am going to define the cell-based approach, which is aimed at reducing the number of costly probability computations. Here I am going to define the cell grid two-dimensional cell grid structure. Let GDB, which is a Gaussian data set, contains two-dimensional objects, and these objects are mapped to two-dimensional space, which is partitioned into cells of length L. Assuming that CXY is any cell, then layer L1 denotes the immediate neighboring cells of cell CXY. Layer L2 denotes the immediate neighboring cells of layer L2, and so on. So the cell pruning. So the purpose of cell-based approach is to identify the cells containing only outliers and only inliers in order to prune them. So in order to prune cells, their bounds are computed, and our bounds are computed by considering the number of objects in cells, the distance between cells and its layers, and using the pre-computed probability values. So if the lower bound of some particular cell is greater than threshold, then all the objects in that particular cell are inliers. However, if the upper bound is less than threshold, then all the objects in that particular cell are outliers. So the cell-based approach is although very efficient, but sometimes it leaves some of the objects unpruned, and for all such objects we follow the naive approach for the computation of d neighbors. So sometimes this approach can be expensive, and therefore we propose a bounded Gaussian approach, or UDB-BG, where we bound the Gaussian distribution or the uncertainty of object to reduce this computation cost. So as we know that according to the 3 sigma rule of the Gaussian distribution, if an object follows the Gaussian distribution, then the probability that that particular object lies within one standard deviation of the mean is 68.2%, and the probability that an object lies within 2 standard deviations of the mean is approximately 95%, and so on. So here we propose bounding the Gaussian PDF, and our purpose is to increase the outlier detection efficiency at a small cost of accuracy by this bounding. So assuming that O.PDF is a Gaussian PDF, then the corresponding bounded Gaussian distribution can be given by this particular expression. Next, I'll give a cell grid structure for the bounded Gaussian approach. So here we take radius r, which is actually bounding the Gaussian distribution equals to T sigma, and we define two regions R d minus Tr and R d plus Tr. R d minus 2r is defined in such a way that if an object lie within a cell CXY, the target cell, and the other object lie in this blue region, which is RD minus 2R region, then the probability that these two objects lie within a d distance of each other is exactly equals to 1. On the other hand, RD plus 2R region, this is the red region, is defined in such a way that if an object lie in cell CXY and the other object lie over here, the outside the region RD plus 2R, then the probability that these two objects lie within d distance of each other is equals to 0. So using these regions, we define some pruning rules by simply counting the number of objects in different regions, and we say that if the number of objects in the target cell CXY is greater than threshold, then all the objects in that particular cell and in the region RD minus 2R are inliers. On the other hand, if the number of objects in the target cell CXY and the region RD minus 2R is greater than threshold theta, then all the objects in CXY are inlier. So these are for inliers. On the other hand, we have the outlier case, like if the number of objects in target cell CXY, region RD minus 2R and region RD plus 2R is less than threshold, then all the objects in that particular cell or the target cell are outliers. Here again, the cell-based approach is capable of pruning majority of the objects, and for the unpruned objects, again the knife computation for d-neighbors are used. This slide gives the complexity analysis of two of the algorithms proposed in this work, and we are comparing it with the naive approach. Here, as we said that the main cost of our algorithms lies in the evaluation of accurate d-neighbors of the unpruned objects. So therefore the time complexities are given in terms of the number of probability computations. And our first algorithm, like both of the proposed algorithms, have an average case time complexities O(n)(n), where n, small n, is the number of unpruned objects from the cell-based pruning, and n dash is again smaller than, it could be smaller than or equals to the total number of objects in the data set. It denotes the number of objects that lie within d plus 2r distance of the target object. So here, as a summary, you can see that the average computational complexity is a bit lower than the naive case, and that is the reason that our approach is more efficient than the naive case. Next, I'll talk about some experiments. Here, for the experiments, we have used 5 different data sets. 2 data sets are synthetic and 3 are the real data sets. And these data sets are normalized to space between 0 and 1000 in every dimension. And objects uncertainty is modeled by the Gaussian distribution, with mean as the object's attribute and the standard deviation sigma. Here, for the efficiency, we compared the proposed approaches with the naive approach, and for the accuracy, we defined like a baseline approach using Nor's deterministic dB outlier detection algorithm, and for accuracy, we are comparing our proposed approaches with the EM's NOR approach. So first of all, comparing the accuracy. Here, the outliers obtained from the baseline algorithm, that is EM Nor's algorithm, are used as the ground truth, and the accuracy is measured using the precision recall curve, as you can see here. And here, this accuracy is computed on the perturbed data sets, where perturbations are obtained by adding normal random numbers with mean 0 and standard deviation sigma p to the tuples of the data set. So here, in both the experiments, one on the real and one on the synthetic data set, we observe that the accuracy in the presence of uncertainty is quite better for the proposed approaches as compared to the baseline approach. Next, I'll give a comparison of efficiency compared to the naive approach. So here, as we can see that even in the presence of log scale, the naive approach takes quite a more time, or it's less efficient as compared to both of our proposed approaches. Especially the bounded Gaussian approach is more efficient as compared to the conventional Gaussian, because it does not consider all the objects in the data set for the computation of their D neighbors. As you know, that since the naive approach is too expensive, also in the remaining experiments we are only comparing the conventional Gaussian and the bounded Gaussian, both of our proposed approaches. Here, these graphs shows the percentage of objects that are pruned by the cell-based approach and the time taken by both by the cell-based approach and the time taken by the unpruned objects and the processing of unpruned objects. And it's very clear that our cell-based approach is quite effective in pruning more than 95% of the objects in majority of the cases, and the remaining are very small percentage of objects which require the naive pruning. Here, like in between the cell-based approach and the naive approach, there's another approach, pruning approach is used, object-wise pruning is used, but it's not presented here because of the short of time. So you can see that the time taken by, although the majority of percentage of objects are pruned by the cell-based approach, the time taken by this cell-based pruning is quite less, as far as the percentages are concerned, as compared to the unpruned objects processing, which is less than 1% in majority of cases, but the time taken is nearly around 100%. So here I present experiments by varying the cell length L, which is one of the parameter. So as you know that the smaller cell length results in tighter cell bounds, and it's quite effective for cell pruning. But for very small cell length, the number of cells increases exponentially, and it becomes expensive computation. Like you can see, when the cell length is 1, this becomes very expensive. And even here you can see that the graph is a bit going up on the conventional Gaussian case as well. And as the cell length decreases, the bounds become looser. However, the number of cells decreases and it becomes a bit effective. So in order to like find the cell length should not be very small and it should not be very large, but in between somewhere. Similarly, we can have vary parameters D and P, and we can have different effects. Like once we increase the parameter D, so it will increase the number of D neighbors, and most of the objects will become inlier. So it has an effect on the number of outliers. Similarly, P is used for the calculation of theta, or the threshold, and it also has an effect on the number of outliers. Next, I present some experiments by varying the dimension D. With the increase in dimensions, the probability computation becomes very expensive, and also the number of cells increases exponentially. So we performed two different types of experiment. We kept our parameter D constant and then varied the dimension. And on the graph on the right hand side, we varied the parameter D in proportion to the average distance between the dataset objects. And in both the cases, we can see that it's still until 5 dimensions, the proposed approaches are quite better or quite more efficient as compared to the naive approach. Especially when we are varying the parameter D, the execution time is far less, because here the number of outliers increase exponentially, because when we keep the parameter D small and objects become sparse, so more and more outliers are actually obtained from our algorithms. But here in this case, the outliers are almost constant for almost all the dimensions. So here's a summary of our first contribution. So as far as accuracy evaluation is concerned, both of our proposed approaches are more accurate as compared to the baseline algorithm. And again, efficiency, as far as efficiency is concerned, both the approaches are several times faster than the naive approach. And UDB-BG, or the bounded Gaussian, is even more efficient than the conventional Gaussian. Moreover, the proposed approach becomes extremely expensive with the increase in dimension D because of the increase in cells, as well as the distance function becomes very expensive, and therefore this proposed solution is more suitable for the lower dimensional data. So here is the publication, two of our publication on this work. Next, I'll talk about our next contribution, that is top K UDB outlier detection. Here again we have three different approaches given for this contribution, that is KUDB, CG using conventional Gaussian uncertainty, and BG using the bounded Gaussian uncertainty. KUDB approximate, here we only approximate the number of D neighbors computed. So here is again a quick review of the KUDB outlier detection definition. So here we try to find out top K strongest outliers, and it is defined as the top K distance based outliers are the K uncertain objects for which the expected number of D neighbors lying within the D distance, we call them D neighbors, is the smallest. So here's again the example, and from this example we found that object 06 and object 01 has the smallest number of D neighbors, and these are actually identified as the top K or top 2 outliers. The motivation behind this work is that in majority of the existing outlier detection techniques, an object is either classified into outlier and inlier, and the number of outliers returned is sometimes unpredictable. Moreover, we cannot obtain outlier ranking in the existing work. So sometimes users are usually interested in the top outliers or the strongest outliers. Even in our previously proposed approach, UDB outlier detection in the previous section, the optimal value of parameter P is sometimes not easy to determine, and if we select arbitrary values of P, it sometimes gives a very small number of outliers and sometimes a large number of outliers. So here, that's why we propose a solution, top K outlier detection on uncertain data, which is not dependent on parameter P. Here's a quick overview of our proposed solution, top K outlier detection. So in the first step, we map the dataset objects to the cell grid like this, and then we create a sorted list, PC list. So this PC list is constructed in such a way that the possible top K candidates are at the top of the list, and the possible inliers are at the bottom of the list. So we can scan only few of the top cells and discard rest of the inliers. And in the third step, like, we are discarding the cells which cannot contain top K outliers. And in the fourth step, we find the top K outliers from the candidates by computing their accurate number of D neighbors. So here I'm going to talk about the steps 1 and 2, that is mapping the dataset objects to cell grid and building PC list. So for the construction of PC list, we made use of region RD minus T sigma. Here again, like the region is constructed in such a way that if an object lie in cell C and the other object lie in this blue region or this region RD minus T sigma, then this probability that these two objects lie within D distance of each other is approximately equals to 1. So PC list is constructed by using this region. So it's a PC list is actually a sorted list of non-empty cells in grid to identify the cells in the sparse region. So this is actually sorted, this list is sorted with respect to number of objects within d minus t sigma region of each cell. So this actually list identify the top cells or the cells containing the top k outliers, or we call them candidate outlier cells. In this step, step 3, we discard the cells which cannot contain top k outliers. So for that purpose, again, the cell bounds are used. So cell bounds on d neighbors are computed for each cell just in a similar fashion like we did in our previous contribution. And PC list is scanned from the top, and all the cells the cell belongs to PC list. Each cell belongs to PC list is either discarded or added to the C cell list. We call it candidate outlier cell list, depending upon its bound. So in the next slide, I'm going to give an example that how it is happening. So any cell, a cell belongs to PC list is a candidate outlier cell whenever number of objects in that candidate outlier cell is less than k, or the lower bound of that particular cell is less than threshold theta. So theta is the upper bound of ck, where ck is any cell in this particular list with the minimum upper bound containing the kth object. So here we start scanning the PC list, assuming that k equals to 5. We start scanning the PC list and keep on adding the cells in the candidate outlier cell list until we find k number of objects, that is 5, and then we set the theta or the threshold equals to the upper bound of that particular cell, and then we keep on scanning the rest of the list, and if a cell is found whose lower bound is less than the threshold, is again added to the candidate outlier cell list. But if a cell is found whose lower bound is like greater than the threshold, it's discarded from the candidate outlier cell list, and it cannot contain any outlier or the top k outlier. So as far as the scanning is concerned, we do not need to scan the complete list because this column and d minus t sigma, this actually behave as a lower bound, and if for some cell in the PC list we find this probability becomes greater than threshold, which is actually the lower bound on each cell, so this scanning can be stopped because all the cells below this level will contain only inliers, or they will not contain actually the top k outliers. So finally we find the top k outliers by computing their exact number of d neighbors. So for the accurate computation, exact number of d neighbors is computed. However, this computation is very costly because in order to compute d neighbors of a single object, we need to compute probability with respect to that particular object and all the objects in the data set. So we propose an approximate approach, and here we are only approximating the d neighbors computation. So from this lemma, as we know that if this alpha or the distance between two objects is greater than t plus 3 sigma, then this probability is approximately equals to 0. So here the main cost of the algorithm lies in this computation of d neighbors, and if we approximate this d neighbors computation, we can save a lot of computation time, as we will see in the experiments section. So here we are approximating the d neighbors computation within d plus t sigma distance of the target object, where it contributes at its most, but after this region the contribution is very small. We also made use of KUDB-BG, or the bounded Gaussian uncertainty, for the computation of top k outliers. And here again the Gaussian distribution is bounded by a radius r equals to t sigma. And here we are only highlighting the main differences between the conventional Gaussian approach and the bounded Gaussian approach. Here the PC list is constructed using the region where the probability is approximately equals to 1, rather than considering all the cells in the PC list. Moreover, bounds are computed by counting only the objects within these two regions of the target cells, rather than all the cells or all the cell grids in case of conventional Gaussian. Moreover, the D neighbors are computed using only the objects within d plus 2r distance of the target object, and we do not need to consider all the objects for the computation of D neighbors, as was in the case of KUDBCG or conventional Gaussian uncertainty. Here again this slide shows the complexity analysis, and here again we can see the complexities of our proposed approaches. The average complexities of our proposed approaches is quite low as compared to the naive case, where small n is the number of candidate objects for the top k outliers, and n dash and n double dash denotes the number of objects lie within d plus 2r distance and d plus t sigma distance respectively of the candidate objects. Next, I'll talk about some experiments, and as far as experiments in this section is concerned, for the efficiency evaluation, we compare our proposed approaches with the naive approach, and for the accuracy evaluation, again we have used EM's NOR approach for the accuracy comparison. So first, I'm going to give some graphs about accuracy evaluation. Here again, outliers obtained from baseline algorithms are used as ground truth, and accuracy is measured using the precision recall curves on the perturbed data set, as was in the previous case, where the perturbations are obtained by adding the noise or the normal random numbers with mean 0 and standard deviation sigma p to the tuples. Here again we can observe that the accuracy of the almost all of the proposed approaches is better than the baseline approach. Next, we give some graphs on the efficiency evaluation. Here we are comparing the naive approach with the top k approaches that we have proposed, and as we can observe that the naive approach is far more expensive than three of our proposed approaches, especially our approximate approaches that are using KUDB approx and KUDB BG. Both are far less expensive as compared to conventional Gaussian, which is considering all the objects in the data set. The graph on the right hand side, we can observe that the percentage of cells considered in the PC list before reaching the termination condition. So here we can see that we do not need to consider all the objects, all the cells in the grid for the scanning or for the scanning of top k candidates, and only smaller percentage, like majority of cases, like around 50 or 20% of the cells need to be considered for the top k outlier detection. So in the next experiment, we will only be comparing our proposed approaches for the efficiency. Here in the next experiment, we compare we varied the dimensions, and as you know that with the increase in dimension d, the probability computation becomes expensive, as well as the number of cells increase exponentially. So the solution becomes, or the algorithms become expensive as far as execution time is considered. Especially you can see like a quite variation in graphs, especially in case of KUDB approximate, and this fluctuation is due to the variation in the number of objects in this particular distance, because in the approximate case we consider the area d plus t sigma rather than all the objects in the data set, and as the number of objects in this area varies, the execution time also varies. So here is the summary of experimental evaluation. So the accuracy of the proposed KUDB outlier detection technique, as we observed, far higher than the baseline algorithm, Moreover, the accuracy of the approximate approach is slightly lower than the conventional Gaussian, but it saves a lot of computation time. As far as efficiency variation is considered, all the variation of the KUDB outlier detection are several times faster than the naive approach due to the strong cell-based pruning and the termination condition. And the approximate algorithm, that is KUDB-BG, and the approximate are faster than the conventional Gaussian using the algorithm using conventional Gaussian uncertainty, since both of the algorithms consider only limited number of objects for the computation of candidate outlier objects. Here's a couple of publications on this research work. Next, I'll talk about our last contribution, that is CUDB outlier detection on data streams. And again, we propose two algorithms, CUDB-CG and CUDB-BG, conventional Gaussian and using the bounded Gaussian uncertainties respectively. And here is the review of the definition. So as we know that the moving objects change their states over time, and these states arrive as time series data streams. Hence we define an uncertain object O is an outlier in a state set as J, where a state set contains the states of all the objects in the data set if its state differs greatly from other objects' state at some time Tj. So the motivation behind this work is like if we use the simplest approach, so we need to perform UDB outlier detection for every state set. But from our observation, the state of all the objects may not change between two time stamps. So this is the wastage of resources if we are performing UDB outlier detection for every state set. So therefore we propose an incremental outlier detection approach, which is based on the change between two state sets. So here the primary cell grid structure is almost same as that of the UDB. However, the cell pruning here, the bounds computation is slightly different. So here layer by layer contribution of number of D neighbors for the bounds computation is required only within the region RD minus T sigma. However, all the objects outside this region, because they contribute very small according to our lemma, they are considered altogether as a single layer. So again, the pruning rules are same, like if the lower bound of in cell CXY is greater than the user defined threshold, then all the objects in that particular cell are inliers. And if the upper bound is less than the user defined threshold, then all the objects in that particular cell are outliers. So here I give the key idea of incremental outlier detection here. So the key idea is to process only the objects which has changed their states during between two state sets, between two states. And we define state change objects are the objects whose states have changed between two states or between time stamps Tj minus 1 to Tj. So assuming that the Cj denotes a cell at time Tj, then within the cell grid, an object can change its state in two ways. Like OP can move to like some other cell, an object can move to some other cell, and the object can move to within a cell. So if an object is moving to another cell, it affects the cells or the pruned cells within these regions, like red and green region. However, if an object is moves within a cell, it does not affect the cells which were pruned in the previous state, because the bounds are computed in such a way that only the cell contribution is considered. So, however, the objects which were unpruned and which required the number of D neighbors computations in the naive case, they are all affected in both the cases. So with the arrival of objects new state, Re-outlier detection is required only for the cells which are affected by the SC objects or state change objects. And we classify the target cells into 3 types. Type A cells, the cells containing the state change objects which have moved to or from another cell at time Tj. We call case in case 1. Type B are the cells in the regions which lies in D plus Rd plus T sigma of type A cells. And type C are the unpruned cells of the grid. Here, as we observe, that the main cost of our algorithm lies in the processing of type C cells, because they require expensive d-neighbors computation. So this cost can be reduced slightly by using the incremental processing of unpruned objects. So the unpruned objects processing require costly d-neighbors computation, and this cost can be reduced by utilizing the d-neighbors computed in the previous state. So for this, a hash table is built to store the probability values which were computed in the previous state set. And at time Tj, or at the current time, these values can be retrieved in O1 time. And these values need to be computed in only 2 cases: when the states of object OP, OQ, or both the objects have changed, or the other case is the probability when this probability is not available in the hash table. So it saves a lot of our computation time by reducing the number of probability computations. Here we also give a bounded Gaussian approach, approximate approach using bounded Gaussian uncertainty, and here again I'm highlighting only the main differences between the CUDB-CG and the CUDB bounded Gaussian. Here the bounds, using the bounded Gaussian, bounds are computed by counting the objects rather than using the complete grid of the target cell. So here we are using only the region Rd plus 2R rather than the complete grid for the bounds computation. Moreover, d-neighbors need to be like d-neighbors of the unpruned objects. They require only region D plus T 2R rather than whole grid or all the objects in the data set, for the which reduce this expensive d-neighbors computation cost. Finally, some experiments. So we have used 2 data sets, TG and MOW. TG is synthetic and MOW is like real data set. And the state change objects are generated by adding normal random numbers with 0 mean and standard deviation delta SC to the fraction of the data set values. And for the MOW, consecutive forecasts are used as the data streams. Here we are only comparing the efficiency. So we compare the efficiency of the proposed approach by comparing them against our own like cell-based method. But in the UDB-CG and UDB-BG, we are executing outlier detection algorithm from the scratch for every timestamp rather than using the incremental approach. So here is the like efficiency evaluation, and as we can observe that as the percentage of SC objects increases, more and more objects move among cells, and more objects are actually SC objects. So this becomes expensive in both in the case of conventional Gaussian and the bounded Gaussian. And when we increase the magnitude of this movement, it also becomes a little expensive, because as the magnitude of the state change object increases, more and more objects move to other cell rather than moving within a cell, and it affects more and more cells, which results in the increase in execution time. Our final experiment results are about varying the dimension D. And again we have fixed parameter and parameter D, where we are varying the parameter D also in proportion to the average distance. And here we can see that as the dimension D is increasing in case of fixed parameter, this solution becomes very expensive. Even our proposed approach becomes very expensive, because number of outliers increases exponentially, or in other words, almost all objects become outliers if we do not increase parameter d in proportion to the average distance between the data set objects. However, here on the right hand side, our proposed solution is still feasible or like usable, and it's better than using UDB approach from the scratch for all the state sets. So here's a summary of the experimental evaluation. So we propose incremental outlier detection techniques which are several times faster than CUDB CM, and the CUDB BG is computationally less expensive because the SE objects in the CUDB BG affects very few neighboring cells. And here's the publication on this work, recent publication. Conclusion. So here in this dissertation, we propose following 3 works: UDB outlier detection on static data, or we can say distance-based outlier detection on uncertain static data, top K distance-based outlier detection on uncertain data, and continuous outlier detection on uncertain data streams. And we perform extensive experiments to prove the efficiency, accuracy, and scalability of the proposed techniques. Here I'll talk about the future work, and as far as the future works are concerned, one of the possible extension of our work is continuous top K outlier detection on uncertain data streams. So we have already studied our continuous outlier detection on uncertain data streams, but if somebody is interested in outlier detection continuously and they are interested in top K outliers, so it is one of the possible extension of our work. Another future direction is UDB outlier detection for very high dimensional data. As we know that the probability computation becomes expensive, and as well as the number of cells become very large when the number of dimensions increases. So we need some techniques like dimensional reduction or subspace mining, and moreover we need to use some alternative of cell-based indexing or pruning to reduce its cell-based cost. Another direction is about UDB outlier detection for other uncertainty models. In the current solution, we have used Gaussian distribution to model the uncertainty. However, other models like the student's t distribution or chi-square distribution can also be used for the same solution. Okay. Thank you very much. That's all. Thank you.
次の時間に入りたいと思いますので、ご質問、あるいはコメントなどからお願いしたいと思います。Thank you for interesting.
Thank you very much, Sensei.
I think your work is fine.
Thank you very much, Sensei.
So I have just one question.
Okay.
About dimensionality
yes.
related to my past question.
Yes.
Please show me the next one and
previous slide.
Future work. Right. Yeah, that's At the preliminary examination,
yes.
I recommended an additional experiment for evaluating your method on high dimensional data. Here, high dimensionality means 10 or more dimensions. But maybe you didn't conduct the experiment.
Actually, in our previous in my preliminary defense, I presented experiment until 3 dimensions, and after that we conducted experiments until 5 dimensions. But after that, like if we keep on increasing the dimensions, this probability computation becomes extremely expensive. Moreover, the number of cells they increase, and it consume all of our like computer memory, even like we are using PC with very high memory. So
my recommendation isn't the condition to get PhD.
Okay, thank you very much.
I guess, but maybe cost experiment is very infeasible in terms of the computation cost.
Yes.
I understand. However, in recent development of sensor devices, the dimension, not the number of dimensionality of data tends to highly rise. For example, my smartphone has 10 or more sensors, GPS, 3D acceleration, temperature, sound, or brightness. In this situation, maybe more dimensionally effective method is needed. So I'd like to know your idea for confronting the dimensionality problem. If you have
our current idea is about like using dimensionality reduction techniques where we drop some of the dimensions which are not very interesting or not usable. And subspace mining here, lower dimensionality is actually used for finding the outliers rather than using all the dimensions at the same time. So these are two of the ideas which are commonly applied for the high dimensional data where like direct high dimensional solution is not feasible. So our idea, or we can say like our future proposed work is more about tends towards subspace mining. It's like we want to work on this direction to tackle the high dimensional data.
But I cannot reduce the dimensionality every time.
Yes.
So maybe simplest method is weak for
high dimensional,
So maybe high dimensional problem you still remains.
Yes, this remains. Thank you very much.
Can I have one comment? I think in high dimensionality, not only the algorithm prediction algorithm itself, but also the definition of algorithm itself should be
modified.
Because in high dimensionality, everyone might be.
Every object becomes outlier. So in that case, I think subspace outlier detection may be one of the solutions where we try to detect outliers in the lower dimensions rather than considering all the dimensions at the same time. But if we consider about very high dimension, even when I performed experiment on 5 dimensions, so we need to increase our parameter d to a very large extent, because considering constant d value, we have the problem of that all the objects were becoming outliers. So here we increase the parameter p to keep the constant, but keep the ratio of the outlier constant. But since we perform experiment until only 5 dimensions, if we are going towards 15 or 20 dimensions, if even increasing d will not be an effective solution, and we definitely need some alternative solution to detect outliers in such case.
So in your algorithm, I guess, so your algorithm is not depending on the definition of distance, isn't it?
Definition of distance.
Definition of the specification of algorithm is not depending on the definition of distance.
Can you work with other kind of distances like Manhattan distance?
We have not studied that, and I think in the current work we have considered Euclidean distance, but not other distances we have considered. But I think if a distance follow metric, then if a distance is metric, that I think our current solution is appropriate and feasible for that work.
So in your case, you assume the noise is derived from the Gaussian.
It
means that the distance should be Euclidean.
Euclidean distances.
But if you consider other types of generation distribution, I think your method can be extended to other types of distances.
Okay, thank you very much. I understand.
Then by changing your definition of distance, the sense request might be resolved or not I'm not sure.
Okay. Okay, thank you very much.
For example, cosine similarity can be used as a distance measure. In such a case, only this distribution should be used for other distribution.
Okay, thank you very much. Thank you very much.
Yeah, I even that Salman sensei had a solutions, similar ideas in previous years.
Thank you very much. Thank you very much.
And okay, my concern is also the dimensions. So to be honest, the dimensions which you deal with in your experiment is too small. Yeah. So and the second my concern is the correlation between different futures seems to be not considered. Okay. For example, could you show the slide of 36? Yeah, which describes the results of the experiment.
This one?
Yeah. So in this case, you used the data with two dimensions, and you say that in the bottom columns, the object uncertain is given by Gaussian distribution with mean and object attribution and standard deviation.
Sigma, yeah.
So I'm interested in how that parameters were used in this experiment.
How these experiments are these parameters?
Yeah. So I guess that mean and standard deviation had to be used in each dimension.
Yeah, each dimension. Like,
Yeah.
for example, like the mean attribute, or like the mean vector. Sorry, the mean vector. If we are having like two-dimensional data, then mean vector will have two values. Similarly, if three-dimensional data is used, the mean vector will have three values, and so on. So,
Yeah,
and
but in case there can be some correlation among the different futures.
yes, correlation.
But in this case, such a correlation cannot be considered.
Actually, as we talked in preliminaries, yes, yeah, we assume that the attributes are uncorrelated. But we studied this there's a method called principal component analysis, where we change the coordinates of the distribution of an object to and this like using this method like principal component analysis, we can transform correlated Gaussian distribution into uncorrelated one. So we need to perform a little of pre-processing before applying this current method or existing method, and after the conversion of this conversion of or using the PCA or the pre-processing, our data would be uncorrelated again, and we can apply the similar technique here.
？Could you go to the slide describing the complexity?
Okay. Yes.
So in your analysis, you claim is that in typical case, the complexity is linear in large n, right?
Linear in?
Linear in large n.
Yes.
N is the number of the examples.
And the small n? The small n?
The large n.
The large n is the number of data set objects here.
Number of objects. Okay.
Number of data sets.
So, and the small n is the number of
number of unpruned objects which were remained unpruned after the cell-based pruning.
So, your claim is the small s is much smaller than large n. So
Yes.
it should be linear in large n, right?
Yes.
Okay. So I think the assumption that the uncertainty is, say, rather small than the variance of the data set, then the small n should be very small, right?
Could you repeat, please? Sorry.
So if the uncertainty of the object
Yeah.
is very small,
Yes.
your assumption holds.
Actually, this depends on the number of like unpruned objects, and yeah, as far as we showed in our experiment that like majority of the objects are actually pruned by like if you consider the cell-based pruning, so more than 95% of the objects are pruned, and thus a small n actually is representing this part. So a small n is the number of unpruned objects, which is usually in our experiment typically is like less than 1%, and this is what we assume, that this is the small n. And as we consider that small n, and like after the pruning, if our pruning is effective, then that assumption yeah holds.
So I agree that this assumption holds for some under some condition,
Yes.
some appropriate condition. But it should be derived from some application scenarios. I mean, actually, in my impression, uncertainty and outlier detection is, I would say, contradicting. So I'm not sure how, I would say, uncertainty in outlier detection should be treated. Because if the data is very uncertain, there should be no outlier. Because everyone is uncertain. So if there is some nice application scenario in that the uncertainty is very, let's say, measured, then you can say that this algorithm fits better to this outlier detection. But in your presentation, you didn't show any application scenarios. So
We showed one application of here, like here in this. So here, like we are assuming that the measurements are obtained from the sensors. They contain uncertainty, and this uncertainty you assume that this uncertainty follows the Gaussian distribution. And here we applied the CUDB or continuous UDB outlier detection technique for the identification of the malfunctioning sensors.
And how was uncertainty of this example?
How was uncertainty
Of this example compared to the variance of the entire example? So we should see the ratio of the variance of the entire example and the variance of the one example to see how uncertainty in our detection is conducted.
Sorry,
For example, if the variance of the entire data set is very large,
yes,
and the variance of one example is very small, it is very easy to find outlier. But if the variance of the data set and the uncertainty of one example is almost the same, it's almost impossible to find out outlier.
yes, I understand.
And I think you assume that the variance of one example is much smaller than the variance of the entire examples. Right?
You mean the skew of the data distribution?
It's not skew, it's the the ratio of variance.
Ratio of variance.
So actually, I'm not saying your algorithm is not good, but just I want to know how your argumentation works in what kind of condition.
Actually, even if what I understood from your question, that if the variance is large, it means like the objects are like distributed, are more distributed, and in that case, like, but again, the current definition holds because we are computing the D neighbors, and we are deciding the outliers on the D neighbors. So even in the presence of large skew or in the presence of large like variance, definitely this example or the current solution will work because it calculates the D neighbors, and if the D neighbors are small, that particular object is actually identified as an outlier.
But the D neighbor, is that mean the D nearest neighbors?
Yes.
So the kind of nearest neighbors can be determined in any conditions.
Yes.
So that doesn't matter, I think. Anyway, this is actually not a question, just a suggestion.
Okay. Thank you very much. Thank you very much, sensei.
So my question goes to the last topic, streaming data.
Yes.
So you didn't mention anything about the memory complexity. How big memory do you need to keep the data?
Actually, here or here, like we only like for example, if we are computing outliers for this state set, so we only need like the computation for this one, like the computation of the one state before this one to efficiently compute the outliers in the current state set. So we do not need the history of all the states because our solution depends only on the previous state rather than all other. So
the point is that you need to maintain the current objects.
Yeah, yes.
I understand, but if we think about dealing with very huge data stream or very huge areas, one computer may not be sufficient to keep the whole data set. In that case, it would be possible to distribute the processing around some distributed nodes without shared memories.
Definitely, if like if the data set is larger than memory, then some parallel or distributed algorithm need to be designed, and yeah, definitely our algorithm need to be modified accordingly.
Basically, you are dealing with spatial data.
Yeah.
You can expect the spatial locality, so you can easily apply some data partitioning technique to maintain that situation. So it may be interesting to see that kind of discussion to further pursue the performance merits.
Okay, thank you very much.
Okay. So you said that you could not obtain good result when using the data with 5 dimensions.
Yes.
But I may be confused. That's strange. So by using PCAs, so in this case you can compress the data. For example, you can decrease the
dimensionality. Yes.
For example, 2 or 3. So if you could compress the data, so I guess that you can compute it.
Actually, PCA.
Why you could not?
Why?
Why you could not compute the data with 5 or 6?
Actually, that topics comes under the heading of like dimensionality reduction. If we are applying like PCA, so PCA is also used for dimensionality reduction. So definitely, like we need to research more about that. Which dimensions need to be considered by computing their PCA or like applying the series of transformations. Yeah, PCA is one of the option for reducing the dimensionality. And then later on, like we can apply the existing technique. But as the sensei said that if like dimensionality reduction is not quite effective, or all the dimensions are quite important, then yeah, then PCA would not be that much effective for reducing the dimension. Yes, I understand that PCA is one of the method that can be used for reducing the dimensions. But currently in our work, we have not applied it for this specific purpose, that is for the dimensionality reduction. And we see it as one of our future work for tackling higher dimensional data.
But in many cases, you're going to need to consider all the dimensions.
Yes.
So I guess that in that experiment where you use 5 dimensions, so I guess that you could use 3 or 5.
Yes, we can reduce it.
So did you try?
No, we did not try PCA method for reducing the dimensions so far.
And I have one comment. So I found that a lot of strong point in your method, but it seemed that there were no description of weak point of your method. So to be fair, you should
some weak points.
Merit and evidence in future presentations, especially in international conference.
Yes.
You should
Okay.
explain all aspects.
Okay, thank you very much. Thank you very much. Thank you very much.